let's get started. So the goal of today is to finish this random variable slides, and then after next week we can we'll continue with the second half of the course. Okay, so I will very briefly review because I think it has been a week. So even for me, I have to take a look before I come today. So I guess it's not easy for you to record everything, but I'll try my best to keep it short. But don't worry, our goal today is not ambitious, just to finish everything in this slide, and then we'll do some exam. So don't worry about that. It's not very ambitious. So that's good. I mean, I hope you can see a band. So the idea of today is random variable. I mean, just to quickly remind you again what's random variable. It's just you have outcome of experiment. You assign number to them. Okay. And there are two things. You assign number to experiment outcome, right? One is probability, right? The other is random variable, right? Probability means representing how likely the outcome is. The random variable goal is to simplify your sample space, right? Because some outcomes you can combine together, right? Just remember the cases. Suppose I gone 2 times, right? Like this one, right? There are 4 outcomes, right? And if you don't care about the order, then you can collapse it into 2, 1, 0, right? Rather than carefully represent exactly what happens, because this is how you measure the outcomes. And because of this, then we have a nice number. Then we can try to say for each number, what's the probability? That is the big P, right? And the other way to represent the big P is the big F, right? The big F is just stacking the P's, right? If you still remember the graphically, right? The P is the probability, and then you stack up, then become big F. And just to remind you a little bit, I mean, when we learn the topic 1, right? When we have a large number set of data, and one convenient way to talk about is the mean and variance, right? Or other kurtosis and skewness as well. But it's also important for random variable, but for our class, we just focus on the basically 2 things: mean and variance, and which actually with what we call expected value, expectation, actually the mean, and also we have the variance. Okay. And we also learn there are several types of way when you talk about discrete random variable, right? By discrete, usually what we mean is like how many numbers you can assign is a finite or countable, right? Either 1, 2, 3, 1, 2, 3, 4, 5, right? Counting. And just to very briefly remind you what a usage of them, because the use case is so important. Remember binomial, right? If you can imagine the future consists of opening n boxes. Each box is a random independent box, can only have 2 outcomes: success or failure, right? Success probably P, and -1 minus P, right? That's called binomial, right? And that is, if you think the future is considered like this, that is the way, right? Because you can imagine that you're doing a binary data, yes or no, right? Whether you like the stuff, right? Whether the consumer like the spicy food example, right? And you consider each consumer is independent, then that would be a right way to model. And the next one, we talk about Poisson. Remember how we use the Poisson? Poisson used as a modeling in a scenario that over a period of time, how many events happen, or how many customers arrive, right? Or how many accidents will happen. So it's over a period of time, how many number of events that is favorable that you're considering, right? And hypergeometric is very similar to binomial, but in the sense that binomial is like each observation is the same probability of success, right? But hypergeometric is not, because you are if you do sequentially, right, it's different from when you have to do things in a collective, right? Remember, hypergeometric is your big N, right? Out of that, A of them is good, and n minus A is bad, right? And you take a small n sample of that and asking how many of them successful, right? It's very useful for audit and for counting, right? Credit control. But I have emphasized when your big N, the whole sample is very big, right? Or you just collect a small sample out of a very big thing, then binomial is also fine. So and that's why some of the book only ignore hypergeometric, just cover binomial and Poisson, because hypergeometric would only matter when you're collecting the sample, the big N, right, is not that large, which happens when you do audit or accounting. And because of many of our classmates, right, are doing from accounting, right, then that maybe finance or credit control or marketing, that would be important. Okay, in that case. So now let me go to the continuous random variable. Okay, and for this one, it's slightly difficult because of the usual tools we use for math have to go to calculus if you do formally. Okay, for our class we don't do it, but we can do it using the similar concept. Okay, we don't do formally for stuff, but I think all the calculation wise should not be an issue. But the main idea, the concept. The main conceptual problem lies on the fact that the big P, right? In the discrete cases, you give me a number, I give you probability, right? The big P roll a die, right? P of 1 is 1/2, sorry, P of 1 is 1/6, P of 2 is 1/6, roll a die of 6 face, right? But you can't really have a P for continuous random variable, right? Because of this. Continuous means it's an infinite number of them, so you can't count it, right? So if you can't count it, then it means that each single number has probability 0, right? Just remember, I don't know, I give the example of this is, it's like I have 5 fingers, right? And if you try to pick a finger of it, right? And there is no problem, each finger has positive probability, right? Because it's fine, no problem. No matter the number you assign, there's no problem. But imagine the scenario, look at the hair you have, okay? If you don't have hair in this room, that's fine. It's not offensive. But so it means if I have particular hair there, I pick this one, I put some color into it, okay? And I close my eye, I try to pick that hair, the probability will be almost close to 0, right? Because it's too many hair. I mean, it's positive, but you can imagine I have infinite number of hair, right? Picking that hair would be almost like 0. So that's why you would use the probability. The P would not be appropriate concept because each one is so small you cannot do it. It's essentially 0. Okay, if 0 doesn't mean philosophically 0 doesn't mean it's not possible, but it's not possible for that specific hair. Okay, so that's why you have to use the big F. Right, the same idea of the idea is like the stacking, right? Remember, if you are at the uniform, if you discrete, right, you still can stack, right? And you can extend it if you have 3 outcomes of uniform. You can also stack there, right? You can imagine I keep going, keeping more outcomes. I can also stack. This graph is remain the same. But the problem of this is the height of this is 1/n, right? When you have many n, then this one would collapse to nothing. Right, so that's why this is not very well defined. You still can define this, right? So that's why we have to define F, right? And as the following, right? Is the F is x less than x. There's no problem, okay? And then we can still say because of this, we can say the probability between A and B is FB minus FA. That's the important part. Right, and this is more than B is 1 minus. So this is basically this graph, right? F less than A, probability is the area under the curve. This is called FA, right? This is 1 minus FA, FB minus FA. We'll talk about this again today. And then how can you define a small f? It's not easy to define at this line because that I think that would be easier is saying that F is defined as the following. for probability between two numbers. Okay, and this probability will be the range, how big this area times the height. Okay, so the probability, the bigger the distance, right, then you just multiply the height. So that is the idea of what you call density, right? Or if you have x, right, add a little bit delta, and over it is with a big F. So the idea is, I hope now I can should not be a big issue, right? I hope you get a pen, right? So just gentle reminder, this x, this f of x, right? And I just draw a line here from A to B, right? And what it said is when A to B is very small, right? This is B minus A, right? I hope this is clear to you, B minus A. And I can pick any number here. I just pick whatever, any x between A and B, right? It's like this rectangle, right? And this, like the calculus idea, with A to B, of course, there's imperfection here, right? But if A and B are very small, this rectangle will be very similar to the area under the curve. Okay, the calculus, if you learn calculus, this is a calculus idea. When this is very small, they're the same thing. So that's why that's how we define. But we're not doing calculus, whatever. But that would be the idea of integration. If you try to see the calculus textbook, but that's not our goal. But you just need to remember the area under the small f. Okay, it will be the probability. That will be how we define. Okay, so although I think it's not easy if you never learn calculus or integration idea, but that is the method we use, and hopefully that will be that will still be you can remember that. Okay, so I mean this already here, so nothing new. It is same as this graph. Okay, there's nothing new here. And again, we have expectation and variance. I'm not going to define it because we never use it. I mean, whenever you use the mean and variance, we're given to you, right? We tell you the formula word, but this is how we get the mean and variance. But that's no different from the summation. I mean, if I look at the technical graph, just same as this, but you replace P by Fx times Δx, and this is actually the integration. So just to tell you that the formula I give you is naturally there's no distinction between continuous and discrete, but we don't need to remember formula, right? But just to remind yourself that what's mean and variance. But expectation is just the mean, right? The average value, right? Variance, how each observation different from the mean. And that's the thing you need to know. I mean, that is no more, no less. Okay. So what the goal today is to go again a little bit more detail on the first three. Okay. And then the last three I will just very brief because they will be used for the second half of our course. Okay. I just state what are they, and then you will see when we use it, then you will know. But the main thing is the first three. Okay. And actually the second, I mean, mainly exponential normal, but uniform is a kind of like you try to illustrate that concept. So to illustrate the concept again, okay, uniform between A and B means that usually we mean the n number between A and B is equally likely. Okay, and later we see why this f is a constant. It's a constant, it's a flat one, because uniform means any number in between is equally likely. So that's why it must be flat, right? Because the area under the curve, right? Under the f is the probability, right? So any in between any interval, as long as they are the same, then share the same probability, right? So that is the reason why the small f is a flat, right? Because any interval, right? As long as the length is the same, with the same probability, right? I mean, maybe I write down exactly what I mean because it might not be very clear, right? So suppose x is here from A to B, right? And this is a f of x, right? And uniform means, right, is I pick an interval, right? Maybe from 3 to 4, right? The probability below is the area, right? This is the blue area will give the probability that between 3 and 4, right? And by uniform means that regardless of where I chose, right? As long as like 6 to 7, as long as this is the same length on the bottom, right? That the same probability, right? That means that the height must be flat, right? Because uniform means no matter whenever I pick the unit interval, no matter where I pick, as long as one unit, they're the same, right? That means the same probability everywhere, right? Maybe I have from 4 to 5 to the same, 5 to 6 the same, right? Or 3.5 to 4.5 the same. So it must be the case, it must be flat, right? Because area below it is the probability, so it's flat. And the height of this must be 1 over b minus a, right? Because the area under the curve is 1 in total, right? So that is the idea why you saw this one, okay? This is the only occasion you need to know the small f, okay? Other than that, for normal, for exponential, you don't need to worry about this, the f, okay? This only case you know the f is a flat, okay? And the big F, right, will be following this one is x minus a over b minus a, okay? Yes. So the idea is just coming from the formula that you learned from the high school, right? The rectangle, right? If you look at this to draw it again, right? Because it's very simple, then we can prove it again because I think we proved many times, but I think it's easy to prove. So x is here, right? What's the area? What's the area of this, right? The base is x minus a. The height is 1 over b plus a. So that's why this x here, the height will be x minus a over b minus a, right? Because that is the idea of the rectangle, right? I hope at this point I have talked about this several times, and it should be clear. Of course, you don't need to know how to derive it, as I'm not required to do it, but you need to know the formula is the big F is this one, right? I don't expect you to remember the small f, but it's good to know. But the big F is something I will expect you to know, right? Because just like for discrete, you should know the big P. For the continuous, you should know the big F, okay? For uniform, I expect you to know the big F. For exponential, I expect you to know the big F as well. For the normal, I don't expect you to know anything. You need to know the table. That is a big F, right? Okay, so that is the big F is what I asked for. Okay, and not me, but I mean that's what you actually need to do the calculation. When you actually apply our model, right? So that's why what I write, right? There will be a number between A and B. This is the F, and this is A. This is mean as a variance. Okay, and I'm not going to explain why there are those, but that is you care the mean and variance. Okay. I'm not going to go to the example because we covered that. For exponential, I think it's worth a little bit discussion because that is a very useful way to model time for things to arrive, and it's very common in business application. Okay, and I guess as undergrad, unless you are data scientist, you use the Poisson to model the uncertainty about arrival of something, no one will complain. Okay, probably if you go to master, then probably you learn more. But as undergrad, you keep this in your head. That is the model to model the time for something to happen as an uncertain or as a measure of uncertainty. I think everyone will be happy about that. Okay. Yeah, I'm sorry for the integration. I should have moved it to the technical part, but you can forget the integration thing. So basically, it's the big F. There's something you care is equal to this expression. Okay, and what I want is this small f. Why I still keep that because this explains what is exponential. Is the curve that's going down like this one, and in the real world, there's a lot of things are exponential. You go to the nuclear plant, the radioactive decay is coming from exponential. The time that things happen is exponential. That is very common in practice. Okay, so So the blue, the purple box is simply give you the idea of how what you need to remember, right? The cumulative F and the mean and variance. Okay, and do remind yourself what is the biggest limitation for this exponential. Of course, for undergrad that'll be fine, but if you want to actually apply in the practice, one of the big restrictions for this is it comes from the Poisson process idea, right? It's like how long does it take for the first one to come, right? And Poisson process is each single minute is independent, right? It means that no matter how long you wait, if things hadn't happened, okay, then the time for next one to come the same. Okay, the most figurative or imaginable image would be you consider the stone on the hill to the seaside. There's tourist attraction where you can often see a fish village where the stone of a woman was waiting for her husband to come back as a fisherman, right? And he waits every day thinking her husband is going to come back, right? And he goes there every day thinking her husband is going to come back tomorrow, right? And there's a strong belief that he should become a stone, right? And the belief is every day, no matter how long she had been waiting, she's believing it's very high probability that her husband is coming back, no matter how long she has to wait, right? Because you expect in general, if he has disappeared for 1 year, 2 years, 3 years, up to 10 years, then the likelihood that actually he is still in the world is very minimal. But if you believe that it's an exponential or follow Poisson, then it's an easy, right? But I would say for business application, for your purpose is not easy because I think that would be the one that we'll use. Okay? So do not be an issue there. So I'm not going to talk about application because I think that would be very straightforward. So what I want to focus our remaining time is on the normal, which is essentially the most important thing for this class, because for the rest of our semester is this, okay? Or his friend T, okay? Or his friend F, okay? So you will see later the T and F are the friends of normal, okay? Basically it's friends and family. Normal, essentially the bell curve. One of the important things to support is any number, okay? Negative, infinity, infinity, okay? So that's different from the exponential from 0 to infinity, okay? This one is from negative infinity to infinity, okay? And I said I don't expect you to know the small f, okay? And the big F, we don't even need to wonder what it is, but you need to know, later we'll talk about Excel or the set table, you need to know how to read the table or use the Excel, okay? So I don't expect you to do any calculation. Quite surprising, right? Because this class is a math class or stat class, and this is the only time we don't do anything. Right? Well, we rely on the computer or table, but it's so common. Or the IQ, or the weight, or height, or later you will see when we learn some theory behind explaining why the bell curve is so common. Okay, but just to begin, look at this F. Okay, this F will be, you have two parameter called mu and sigma squared. Okay, so two number, and as you might expect, mu is exactly the mean. Sigma is the variance. The mu control where the peak of the bell, and sigma is controlling, you can say the height, but or usually how flat it is, right? Or the how damped or how squeezed the bell is. Okay, the higher the sigma, the more spread out, right? Do note that the area under the bell is always 1 because that's probability. And although I put a purple one, I'm not expecting to remember this, but I put it there because it's so important. At least you see this, you know it's normal. I mean, I'm not expecting to memorize it, but at least you have some idea. There's some square, there's some pi, there's an e, then there will be square, there will be normal. But that is the only thing you need to know. Some idea of a bad guy or the good guy, whatever. I mean, whether you like it or not, but that is the thing. Okay, the mean and variance, as I said, is mu and sigma square. Okay, so it's symmetric. The skewness is 0, and kurtosis is always 3. That means excess kurtosis is always 0. That would be the thing. And just to remind you, why we use normal, or when we use normal, is when we do a lot of financial data. The first round approach is to consider it's normal. Okay, and that is behind the very famous formula, the Black-Scholes formula. If you know how people how to pricing the options, that is called the Black-Scholes option pricing. Okay, of course you may ask, is it the normal? Is it the most appropriate? Given we have so much advance in the data science, still normal is one of the best. And of course you can replace your other thing as well. But although the bell curve looks not very beautiful, but if you're able to handle the math, actually it's pretty easy to handle. Okay, although it's not have no closed form, but still things actually is easy to handle. And you can look at the risk management, the value at risk, they all use normal, and quality control, normal is very common. Okay, I hope I don't need to convince you why we use it, but you know it, we use it through the second of the semester. And here is a very the notation. Okay, we will have the notation for the rest of our class is what we call X follow a normal distribution with mean mu sigma square. Okay, you can read it as follow a normal distribution or distributed as normal, whether you there is a notation. Okay, and here comes a very important idea we call transformation, which essentially is a very special property of normal. Okay, this only holds true for normal. To remind you again, it doesn't hold true for anything. Okay, in general is not true. Okay, what it said is if I have a normal distribution, I multiply by constant plus constant to a normal. Okay, and you can see because normal can be negative infinity, positive infinity. So that is why it still works, right? If exponential add something, it's no longer exponential, right? But exponential start from 0, right? You add something, it's no longer the thing you want to do. But anyway, it means multiply something plus something, still a normal. Okay, this mean and variance come from the idea of the mean and variance. Doesn't rely on normal. Okay, the only thing is new in this statement is the normal. Okay, and why is important? Because when you put A is equal to, okay, negative B over A, okay, then this imply, okay, becomes CO1, okay, because it basically just like the idea is the following, just to draw it to make it easier to understand, hopefully, is the idea is like this. I have a X, okay, and X follow mu sigma square, okay, the standard, any normal you can imagine. But now we have a Z, okay, Z is what? Z is normal CO1, okay, and look like this maybe, okay, and the mean is here 0, and the mean is here is mu, okay, and possibly the question we usually would care is the big F, right? Suppose we care about the big F. I pick a particular number here called A, okay, or called X, right? Called X, okay, small x. Okay, I want to know the probability here, right? That is F of X, right? Is that it? How are we going to do that? Okay, and this idea of transformation tells us if I look for the following, okay, which is x minus mu over sigma, okay, and I look at this area, okay, this is, let's call z, okay, small z, this is f of z, okay, these two areas are the same, okay, that's the math behind, and that's the reason why we look at the z table, okay, all the time, because of, you can of course do this calculation, but you can always transform from x to z by subtracting mu over sigma, then they're the same thing. So that is the main idea we look at the z table. It's because of you can switch back and forth, right? And why this is good, because you don't need to do the computation every time. You just need to know how to do computation for this standardized one, the standard one. As long as transform this, and you're done, right? Because remember what we're doing. We're looking at random variable. What is the use of random variable? Is to look at the probability, quantify the future, and we want to calculate probability by f of x. So the f of x is the thing we care, and we transform it to the z, then we're done. Is that clear? I hope that is clear. Don't worry, it should be clear, because as I said, you'll be doing this again, again for the rest of semester. It's hard to not to know, because the worst thing from this class is look at the table, so you remember. Okay. So usually the table you get is two versions, either less than 0 or more than 0. Okay. But let me show you. The table we have. Okay. So let me do it again. So I look at the number that is z is less than 1.4, right? So remember, the table is the big F, right? F of z less than 1.4. So you will be looking at the z table, this negative one and this positive one. I look at 1.4. How I going to do that? I go to the, look at the row first and look at the column. The row, look at 1.4 is here, because 1.40 then will be this one. If 1.41 will be here, if 1.42 will be here, so on and so forth. Okay, this is 1.40. Okay, for example, if I have this last one, the bottom right hand side will be 2.09. That will be this entry. Okay, remember this gives you the F. Okay, so it's an area on the left hand side. Okay, so if you want to find the right, one subtract. So that will be the idea. So the same for this, negative 1.6. Okay, and one of the easier way is look at directly from the negative 1.6. Look at negative table. Negative 1.60 is this guy, right? Once of that, you're done, right? And that would be the idea. Okay, I think this table have some mistake. I'll upload the new one. Okay, this table has some mistake. But anyway, I should have uploaded the new one, but I don't know why it's still old. But I'll update it today. There's some problem with this table, but I'll update it. So from that table, what we learn is one very important rule of thumb, right? Because just to go back to this one, okay? I guess it's good to mention this right now is what's different x and z, okay? X is looking at the exact value, right, in the bell curve, right? But what is z here? Is z looking at how your number, right, is relative to the mean mu, and is the distance is measured by how many SD, right? So when we have a set of 1, that means that it's 1 above SD, right? If I z is 2, it's 2 above SD. if Z is minus 1.5, it's 1.5 below SD. Okay, so basically, is the bell is a raw data, but you're talking about we know it's a bell, so we can every time we can talk about how many SD above and below the mean. Okay, so why is that important? Because this gives us the idea of the bell important fact is called rule of thumb, and probably this is one of the things that if you took this course after 2 to 3 years, you probably still remember this one. Okay, this is the rule of thumb that naturally probably the only thing you will remember from this class if you are not doing anything. So that is mean that for the bell, will be within 1 SD is 70%. So look at data. If you within 1 SD, there will be 70% of data. Okay, and 95% actually within 2 SD. Okay, and 99% between 3 SD. So look at this graph will be like this. Between 1 and 1 is 0.68, right? And 95% actually within 2 SD. Okay, and 99 will be 3 SD. Why is important? Because later you will see we'll do a lot of time is if everything is between 2 SD. Okay, right? So that will be the way we do decision. Then later you will see one of the important applications is called hypothesis testing, which is saying that, right, since things within 2 SD is considered to be normal, 95%. If things are beyond 2 SD, then usually we call something exceptional, right? Suppose we have a IQ on average in the population is 100, right? I think Hong Kong is a little bit higher. I think it's 110, okay, 110. And SD, if I remember correctly, is around 15, right? So if a kid, like many of you, you guys told me it's a kid, right? Anyway, then is within, okay, if you're 100, right, within 130 to 70 is still considered normal, right? If you beyond 130, then you are considered to be part of the genius group, right? So that would be the idea, right? Or you can imagine doing investment, right? Collecting a bunch of stocks. Look at the return. Look at the SD of the returns, right? If your return is way above more than 2 of the mean of the SD, right? Then actually that stock is very exceptional. It's very good to invest. If it's below, then it's underperforming. Okay, depend on whether you want to invest in a dog, right? Or you want to invest in a very hot stock, right? You can decide what to do, right? Probably something in the middle, probably don't care, right? But something is like extreme, then you will care, right? And later you will see this 2 SD is the single most important thing that you remember, because you always want to check is more than 2 or less than 2, more or less, like, or to be exact 1.96, but anyway, it's more or less 2. But later you will see. Okay. So the last one to talk about before the break is called inverse normal. Okay. Inverse normal is the idea is very simple. Okay? There's nothing new here. Okay. And what we have is this, right? I have a Z, right? Z is actually normal 0, 1. Just to remind you, what's that? It's 0, right? And the F table tells us what? You give me a number, I give you the area on the left. Okay? You give me a number, I give you area on the left. So that's the idea, right? So a number here, A, whatever. This is the number. Okay? Right? So you give me this. Okay? I give you this. Okay? That is the F table, right? You give me A, I give you F of A. Inverse means you give me F, I give you A. Okay, just reverse it. That's called inverse. Okay, you give the area on the left, I give the number. Okay, that means you give me 0.5, it will be 0. You get that? If you give 0.5, it will be 0 because symmetric. This is halfway. Okay. So don't worry, this is actually you don't need to worry about that. This will appear in your Excel formula. All right. But what does that mean is super simple. Go back to the table. Right. So you give the number, say 0.815 line, then go back, look at this number, go back, is 0.9. So you just read the entry and go back to the number instead of going number to this reverse. Okay, let's give us one example. Give a break. So don't worry, I'll give you a break very soon, so I don't take away too much time. So this is 0.95. Okay, I want the area on the left is 0.95. Okay, you do this all the time. So how do you do this? Look at the table again. What is 0.95? Okay, 0.95 is table. Look at this humongous table. How can you start? Okay, just look around. 0.95. Okay, must be 0.7 is too small. 0.96 is too little. They go up a little bit. Somewhere here, 0.4 and 0.5. Then look around. They look around. Somewhere here, 0.4, 0.5, right? And it's 1.64 and 1.65. And usually, how you do it, just take the average. You don't know which is the middle. So that's why usually you have 1.645. Okay. For us, doesn't really matter. Just take any number in between will be the same. Okay. But don't worry, you use Excel, right? Then just the number you can easily give, and you will see later. When we talk about Excel, you can get Excel number. But if you happen to use the Z table, any number in between will be fine. Okay, is that clear? So let's have a break of 15 minutes, and after the break, we'll finish the rest of the slides, and then we will do the Excel. Okay. So a break of 15 minutes. I'll open the reply so that you can tell me whether I should emphasize some of the part that you may not feel comfortable with. Well, break, please feel free to do it. We'll resume at 35. Oh, no. You can ask me any question during the break and go around to see if any question. How long? And after the weekend, no one has come. I don't say that will come. I'm looking how long for you. Technical is like this. If you want it, just want a definition, it's like that. probability x same as probability x given x is greater than a number. So I tell you that I have wait for 10 minutes. Doesn't change our idea. But anyway, I don't know. What I mean. And then I tell you that you have wait for 10 minutes. Doesn't say anything. Right, you go home, right? So you maybe never go home. Then you are exponent. You say exponential, but you go home, right? So that's right. There is no aircon, it's very hot. Right. Okay, can you hear me in the back? Good. So let's see whether anywhere I need to emphasize on. Yes. So please take your time to review your stuff, and I think our TA have usually have Friday afternoon. Yes, an office hour. Talk to him. I think it's our TA. You could try to ask him. I mean, he's very kind and gentle. So please feel free to talk to him if you have questions. Oh, can I explain the more idea? Okay. Yes. So the idea is like this. Okay. Suppose the inverse is like this. It's just reading the graph. So I want to have say, okay, that's that the CO1, right? The question like this. Suppose I want to find the area, okay, is 0.5. What is this number here? Correspond to the area on the left is 0.5. Okay, that's the idea. Okay, let me repeat the statement is I tell you the area on the left. I want what's the number in the bottom. Okay, F is the follow. F is I give the number at bottom. I tell what's the area on the left. Okay, that's reverse. Okay. So to do it, what I'm going to do is look at either table. Okay, the table tell us immediately. Make it bigger. Okay, is on the very upper left corner. Okay, right. Look at that. It's 0.00. So that's 0. Okay. Or if you want the area on the left, it's like, say, another example, maybe make it a little bit non-trivial. Suppose I want to look at the other example is what I want is say, I use other color. Okay. Again, is Z. Okay. I want this is, I don't know which number, but I want this area is 0.7. Okay. So the question is, okay, I want the area on the left is 0.7. And I know must be positive, right? Because middle is 0.5. So I don't know where the 0.7. So we're going to do is look at the table again. 0.7. Okay. Don't make a mistake using this one. Okay. I have to read here 0.7. I screen 0.6, 0.8, so somewhere here. Overrun. Okay. Somewhere these two numbers. Right. So it's 0.52 and 0.53. So between I will use 0.525. Okay. Or any number between 5. So the method for calculation. Unless you are doing a very important science, that will be method for us, right? So then we matter anything. Okay. Is that clear? I hope that is clear. If not clear, then we'll do more example later. Okay. Yeah, those equations look so complicated. Not sure which one complicated. I guess you say the normal thing. No, we don't need to remember the normal, right? The equation you need for the continuous, right? Remember the formula. What we have with the blue one, right? Only know the mean. Of course, this one is a little bit complicated, but mean and variance like this, and that's what we know, right? We don't even need to worry about it, right? And for this formula, it's just like, you know, the exponential, there's a big F like this, right? So we don't need to remember, right? So it's open book. So I guess even though complicated, as long as you know where the plot is. And just like all the, as I mentioned, right, there's an analog, right? The iPhone, the smartphone app, right? The behind the code is very complicated, right? But you don't need to worry about it. You just need to know, you click this button, you do what, this button do what, and you're done, right? You need to know why it works, right? Nobody actually know anything how anything works. You just know this button will have this function, this button with this function, then you're done. Later we do the Excel, tell you which button and which function, and you know how to use this is you're done, right? You don't really know how to do it. Yeah, too much reviewing. I agree. but we're still within our schedule, so don't worry about that. So we were able to learn everything we said in the course outline, so don't worry about that. Although it's slow, but I make sure everyone is there. Okay, today is first day to make sure. If you don't remember, it's not Wednesday. Today's rainy, I agree. Sunny, I don't know, maybe. So even though I have too much review, and you can see that still people, most of people think I'm in the middle, so it's still, I mean, might be a little bit okay, not too slow. So it's okay. I hope that is fine. I hate midterm. Yeah, I think I do. I mean, I mentioned that's why this class is on midterm. I hope that will be fine. Now maybe we give more example on how to do the X and Z problem. So give you this problem again. Okay. This will be the usual problem you may imagine, right? So X follow the normal distribution of mu 20 and sigma 16. So I mean, although I put it normally, imagine this like the stock price, right? Is mu 20 and sigma 16, right? Or I have a I don't know, it's IQ, let's say everything is there, right? Or the quality control, whatever, everything is normal. But because remember, although I didn't put it there, but it's easy to imagine binomial or Poisson or whatever turn out to be if you're very big N or Poisson have very big number, binomial big N, everything actually very similar to normal. We don't prove it, but you will see, we will mention it later. Okay, but normal is very common. So what we want is like this guy. Okay, we want X is less than 16. Okay. So I'm not going to go to the calculation, but instead I tell you the what is asking, right? So the question is like this: the bell follow a normal distribution with mean 20, sigma square 16. Okay. So sigma square being 16, sigma is 4. Okay. So this is 12. This is 16. So the question is asking this area, right? Because asking probability X less than 16. Okay. And what we're trying to do is the Z is a normal CO1, right? So that becomes 0. And what's this one? Okay. What's 16? 16, right, is actually 1 SD below the mean, because SD is 4, sigma is 4, right? So 16 is 4 below 20. So guess that is -1, right? If you remember, how you transform this is X minus mu over sigma, right? So it's just 16 minus 20 divided by 4. Negative over 4 is -1, right? So this red area is same as this pink area, right? So you are able to answer the question, as I said, is the stock price, right? On average is 20, have variance of 16. You're asking how likely that is below 16, right? Then it's just transforming to how likely is 1 SD below, right? It's this area. Look at the graph, you can check, right? Let's check this for once more for you. I'm not going to do any stat table, okay? But I think you should be able to do that. So it's -1 on 0. So -1, is 1.587. Okay. So I hope that has become clear. And more than 24 will be the same, right? Because 24 is just like the SD is just 4, so it's how more than 1 SD, right? Just to draw a graph again, I'm not going to do the detail, but hopefully that will give you the idea, right? Instead of 20, the question asks you the following: 24 here, right? Asking this area, but this area is essentially this area 1, right? And how we do that, right? Because actually we don't need to do anything because actually that's symmetric, right? The pink area is same as the black area. Of course, we look at f of on the left hand side 1 and subtract on 1 the same thing. Okay, so I'm not going to do the detail, but I hope this is clear what's going on. Okay, so I will be now basically you learn everything. So I little bit speed up a little bit because what is left is just kind of bunch of facts which we'll use to give you logic behind in the coming chapters. Okay, it's not technically not belong to this chapter, but I just include here because for completeness. Okay, these are the facts that we'll use in the future, and we don't prove it. Neither for any other class will prove it, but just put it there. Okay, what it said is if I have 2 bell, add up is still a bell. Independent. Okay, so note that this is not true for any other system. You add 2 exponentials, not exponential. You add 2 binomials, not binomial. Okay, it's almost never true. But surprisingly, for normal, if you add 2 bell, it's same as a bell. Look at this diagram. Okay, I have a bell of a light blue and a bell of a red. Add up is a deep blue bell. Okay, and this is very surprising because it never true. It almost never true for all the scenario, but true for normal. Okay, the bell is have a very special property, and that later you will see that's why we often see bell. Okay, but later we'll talk about that. And the next one is saying if 2 bell, not just subtract, not like add, subtract is the same, right? Because actually we didn't say what is the mu. Mu is the negative, so everything just carry from this. Okay, so right. So I have a blue and red. I subtract. Just move the mean. Okay, the variance still larger. Okay. So this we'll be using this way often when we talk about it later because when we do sampling, there's an idea because adding will be we will talk about that, but not our concern right now. You just need to know this is the fact. That's it. Okay. Now here comes the several facts you need to know, but you don't need to worry about that because we'll talk about it later. Okay, but just say it now. You will not be too surprising because they are the only the chi-square, T and F. We'll use it in the later stage. Okay, I just put it here to tell you what are they, and then go to Excel. Okay, there's nothing. You don't need to worry about this because we know using it for your assignment or work. But just say there, you learn it or use it. Okay, and we don't even go to what are they. Just you use it. We tell you when to use it. Okay, and chi-square is not using in our class directly. Yeah, some other class we will, but in our class we not. And you will see why we learn this chi-square. Chi-square with the basis for the T and F in the next 2 slides. Okay, what's chi? Chi-square is very simple. It's not difficult. It's basically derived from the bell. Okay, what it said is I have a bell. I take a square of the bell. That's chi-square. So what does that mean? Very simple idea. Look at the following. Now I have a bell. Okay, this bell is their normal. Okay, so what I'm going to do is M.Phil. I try to draw one number from this bell. Okay, suppose I draw 1. That's square. Still 1, right? If I draw number 2, the square becomes 4. If I draw a -3, that will be 9. Okay, and what we will get is called chi-square. It will be coming from 0, something like that. Something like that. Okay, you will see the graph in the look like this. Very looks very much. But I'm good. Look very much like exponential. Okay. And y equal chi-square. It's a typo. Supposed to be x squared, but in the old days, right, they pick the stamp to print. The one who picked the stuff is wrong. They pick the wrong thing. They can't distinguish chi and x, so that's why I end up with the chi. Okay. Chi is I think it's a Greek letter of x. But anyway, just x squared, just standard normal square. Okay, and that's called chi square. And probably you will see, we have a chi squared degree of 1, and n will be just add up. Okay, so what does that mean? Chi squared n is I have n pair. I take one number from each pair, I square add up together. That's chi squared. Okay, maybe easier to think. What is chi squared 2? Is I have one pair here, I have one pair. Okay, I take one number from one pair, square it. I have another pair, square it, add up. The number I have, chi squared. Okay, and we don't need to worry about this because we never use it directly. It's all in the background for our class. Look like somewhat like chi square 1 look like this, chi square 2 or 3 look like a little bit skewed, but when you have higher chi square, actually you have a well bell shape. Okay, and actually chi square many look like very look like that. But anyway, it's not a concern. But anyway, this is the chi square. Don't worry about this chi square. You will never use it directly for our class. Okay, just to give you we use it because this gives our definition for the t, which this t we'll use it for a lot in the second half of class. Okay, the idea of t is the following: we have a standard normal, okay, and a chi square m over m. Okay, and take a square root, and this crazy thing equal to the t. Okay, I will first tell you what t looks like first, and tell you why we did that. Okay, this one is actually a bell, but let me show you the graph. Okay, the golden one, t infinity, will be actually normal. The less n will be a much better tail. Okay, so basically in your mind, just remember t is a bell with a tail. The closest is more than 3. Right? So for you to remember just one thing, and then later you learn the t very soon. But you didn't remember for now, it's just t is just a bell with a better tail. That's it. Okay, and if you really want to know more, but which for those who have studied math class, you will be extend normal over the square root of chi squared of m over m. Okay, later you will see why we do that. The reason is when we collect data, the sample mean actually follow this. Okay, later you will see when we learn that when a sample size is large, normal will be fine. But when someone is not large enough, but you will see clearly why we do that. So don't worry about that. Basically, just the sample mean over the sample variance. That is what we're doing. Don't worry about that. You'll be very clear later why we need that. But in a moment, just remember t is just a bell or a better pair, and we will use it. We'll need you to tell you when we use it instead of normal. Okay, and the reason is sometimes using normal is not right. It seems somewhat numbers not right, and you can adjustment using the t. Basically, is when to be easier to think is when you collect sample to do analysis, the sample size is not big enough, then use this one. If sample size is big, then you can use normal. Not big enough, you use t to analyze. So that is a shortcut to what we're doing. Okay? And that's why we will be using this t all the time later. So don't worry, that's what you need to know. Okay. Lastly, don't worry about this. It also looks crazy. F is a chi square of m over chi square of n. Okay, and you will say, okay, what I'm doing here. Okay, chi-square is equal to variance. So basically, this is asking you compare two variables. Okay, the application will be later using the F test is I have two, say, stocks. I want to compare is the stock A and stock B, which one is more risky, right? I want to compare the variance. And that's F we'll be looking at. Okay. And that was the reason why we do. Don't worry about it, we will use it when we at the last three topics we talk about F. Okay. And just to remind you that F actually has two numbers. Okay. So it looks like either a exponential stuff or look like a tail. And then you don't need to worry another shape. Okay. Because I can't remember anything. So just draw it to let you know that would be something, some shape. To make sure that sounds familiar. Okay, you don't need to worry about that. So for this class, for this topic, so we don't need to worry about the chi-square, T or F because we'll mention it later. I just put it here because to be complete this thing because everything is self-contained. When we learn, then we come back. Okay, so don't worry. Is that okay? I mean, I know I have thrown you a bunch of stuff without explaining, but just to let you know these are the things that you'll be using for the rest of the time. Okay. So if no question, then we'll turn on our Excel. So don't worry. The Excel is super simple. Okay. Basically tell you how to apply the formula. Please open the Excel. It's not hard. Okay. So we'll try to go over the functions. Okay. Don't worry, it'll be very simple. I guess even though you don't need me to talk about all this, but just go over that with you. Make sure that you understand the syntax. Okay. Nothing new here. So here, if you still recall, the binomial question is, I have a restaurant. Each customer has probability 0.3 that he likes spicy food. Right? The question is asking, what is probability 2 of this customer out of 5 like spicy food? Right? If you remember the Poisson, right? The formula we have is like 5C2, 0.3, 2, 0.73, right? So this is the answer, right? Just forget, look at the slide, it says there. Of course, I expect you how to know how to write that down. But how do you do it in Excel? It's very simple. It just use the binomial distribution. 2, 5, 0.3. False. Okay, what is false here? False give you the P. True give you the F. Remember the example? P is giving exactly 2 people. Less than equal to 2. Okay, let me show it to you. To the Excel. Is that okay? Okay. So don't worry. I guess shouldn't be hard. With Excel part, even though I don't talk too much, you know. Okay. It's binomial. Okay. As I said, I'll upload this Excel by the end of class. N is 5, right? And P is 0.3, right? And X is 2, right? And I want to have P of X, right? And F of X. Okay. So this is the question, right? Look at the green box on the slide, right? Exactly 2 will be just binom this, okay? And B3, X, right? Number of trial is N, this is P, and this is false. Okay? False will give you the okay, let's go around because I will be slow for this one because every rest the same. I just want to make sure that you know how to handle. Let me know if you don't know because the rest will be very similar. Okay. Let me know. Don't worry, you're very confident. calculate that, and it should be very clear from what you should expect is this number. Okay. So you put X and P. That's it. Right? The force is just to give you the P. Then you can also have find norm this, okay? And I also have the B3, B1, and B2, okay? But this one I have F, right? So I will do the true. So remember, right? We have 84% of the customer that out of 5 people actually less than equal to 2. So I hope this is clear because the rest will be very similar. Actually, even though I don't go over the rest, you will not find it. Is that clear? How to do the big yeah. Is that okay? I don't want to rush because that's very simple. In case I lose you, we can still continue next week. The Google Sheet code also can do the same. So the syntax is the same. So even though we don't like Microsoft, we like Google, so the same. I don't know Mac, their own version, but at least Office 360 or the. Is that okay? Now I know, and let me do the Poisson with the same idea. Okay. Poisson is again just the Poisson, right? You put X and lambda. Right? The question is asking, remember the example is there are 5 customers arrive in an hour, right? Asking exactly 2 arrive, right? If you remember the formula, actually this is this guy or this guy is doing this, right? E to the negative 5, 5 to the power 2, and 2 factorial, right? So this is the formula, right? E to the negative lambda x. Okay. Formula. I need to show you this is why exactly this number is this one. So let me show it. So let me do another slide. Okay. Let me do another sheet. Okay. What I do is lambda number 5. X is being 2. So I want f p of 2, p of x, and f of x, right? So it's very simple. Just 2 numbers, right? Poisson is only one simple thing, just lambda. Poisson dot this, put the x, b2, and I put the mean, which is lambda, and I put false, okay, because that is the p. Is that okay? So I hope you would guess how to do the f. Shouldn't be a big issue for you. Okay, will be the same. Poisson this b2, b1, but now I become true because true is the big F. True and false is just asking whether it is going to be a last. Definitely. Is that okay? So this will be the answer. Let me save the file first before I continue because I worry about. Okay. Is that okay? same answer. Okay. Now then try a little bit more. Okay. Now what I want to do now is the hypergeometric. Okay. Hypergeometric has 3 parameters. Okay, which is N, A, N. Right. Remember this example? We have 30 items in the warehouse. Out of 6 is good item, defective item, right? Successful item. And the rest will be the bad item. And we are going to, 30 items out of which 4 is good and 26 is bad. And now we draw 6 items here. And we ask exactly 2 of them is belong to the defective item. Right? So, and this, remember, is what? Is actually doing, you can verify, is out of 6, right? You have 2. Sorry. Out of 4, you have 2, right? And out of 26, you got 4 here. And this is 30 over 6, right? Right? You still remember what we're doing, right? So let us do that in the Excel. Okay. So we got hypergeometric. Okay. We have N, and NAN, I guess. NAN, yes. NAN X, okay. And we want for the P of X and F of X, right? And is we take 6 items here, right? And overall we have 30 items, out of which 4 is considered defective item. And we want to calculate popular 2. So that is a question, right? You still remember how we input this number, exactly same as the slides. So there will be hyper geom. Okay. This we will put X, right? And then N, A, N, and then false. Okay. So that would be the answer. So let me do again for the P, right? Would be N, N, N. Okay, so that would be ideal. Okay. That 2 exponential normal. Hope that is clear how to do. Okay. From this slide, and upload it yourself. Fun. Don't worry, if you get it otherwise, be fine. Okay. So now I hope it's okay. We will do exponential. And exponential have to be slightly careful because the way you input is input 1 over lambda rather than lambda. Okay, so depending on how you specify it. So Remember the question we have is, we do not care about small f or other big f. So we didn't write this one. This is only the true one. Okay? I mean, the question for this one is, on average, you need to have 20 minutes before someone will come in. The question is asking, less than 10 minutes, the guy will come. Right? So if you still remember the formula, which if you check the slide, you'll be like this, right? This is this got to be 1 minus e negative 10 times 1 over 20. Because lambda is 1 over 20. Okay. So let us go to this one. Okay. Lambda is 20. Okay. And x is 10. Okay. And I want to find fx. Okay. And we're going to do slightly little bit trickier. We'll have a exponential distribution x. Okay. The lambda they have is different from lambda I have. That's fine. So 1 over that. So have to be 1 over this guy. Okay. And then I say true. So this is the one that M.Phil. Is that okay? Yeah, I think it's already implied. But the only thing you have to be careful, the lambda is have to 1 over. The way I do it, the lambda, the way I do it is because I try to be consistent with the exponential, but they use the 1 over. Okay, is that clear? The only complication I mentioned is the lambda I use. The notes is 1 over lambda. The reason why this is that every textbook has a different way to mention it. I just use the one that consistent with our horizon, so you understand the relationship. Okay, is that clear? Now we are going to the very last one, which is normal. So don't worry, that will be simple. Normal, our last one. Normal, that is set table. And the good thing about Excel is they do the standardization for you. So you put 16, 24, give you directly the answer. Even better than set table, right? Set table actually means this is 0, this is 1, right? But they do the conversion for you. Because you need to subtract the mean over the SD and then do calculate. But Excel, yeah, they do it in the background. Okay, they do it for you. Okay, so let me show you this one. That is easy. Okay, so what I want is mu sigma. Okay, I think it's sigma square. Sigma, yeah, sigma. So mu is 20. Okay. Do note that this is sigma, not sigma squared. Okay, this SD is 4. Okay, so x is 16. What is f of x? Okay, so it's very simple. Just norm this, okay, of B3, right? And then the mean and SD, and then true. And that's it. Then we're done. Okay, so that is the answer. Now you see, very simple. Nothing. That's what we need. Okay. You're done, then you can go. Sorry, time. I will see you next week because Monday is a happy holiday. And do remind you that we missing Monday. We have a makeup class, which is optional on Python on the Tuesday and the Wednesday. Okay, optional. You don't have to attend. Attend to be on the B.A. lab in this building. It's already on the announcement on the platform. So if you want to come, you come. You don't come, it's fine. The 5 point not in exam or it's optional. Okay. I will see you next week. Enjoy the weekend. Long weekend, kind of. Hi. Oh, I forgot to switch on this. Okay, fine.